All right. Thanks very much, and good afternoon, everyone. So what I'm going to be talking about today is the perception of latency and latency in touch systems. And in particular, what we're talking about is interface latency. And that's defined as the time difference between a user's input to a system and the system's response to that input. And you can see here in these videos of existing consumer devices that there is quite a bit of lag that is present. And it makes sense that this lag is there. There's a lot that has to be done. Hardware sensors have to be read. The results of those sensors have to make their way up through a variety of layers of software until they get to the application, which has to figure out what to do, update the display buffer, and wait for the screen to refresh. And despite the march of Moore's Law over the decades, there's still considerable latency in consumer devices. And in fact, they tend to range at best down to about 50 and at worst up to 200 milliseconds. And not only is this noticeable, it actually can have an impact on performance. As just one example, there's many studies that have looked at this. Jota et al. Found that a 50 milliseconds of lag can have a 20% impact on Fitts law performance. So it's a pretty significant impact from not that much latency. Moreover, there's a user experience impact as well. And we think it's similar to the impact that changed about 5 years ago as we started to move from lower resolution screens to the very high resolution, or retina if you like some companies' branding, of displays. What used to seem like a really good device suddenly seems outmoded and awful as soon as you set eyes upon something with the high resolution screen. And we think it's a similar impact of ultra low latency systems. Your phone may not seem that bad now. As soon as you try one of the ultra low latency devices, you wonder how you've ever lived with the existing thing that you have. Now, to be clear, our goal is not no latency, because that's impossible. Our goal is simply to have no perceivable latency, which is a much easier engineering challenge to try and undertake. But to do this, we need to understand what it means for latency to be perceivable. And that drove us to the two questions that we looked at in the paper that we're talking about today. The first is, what are the lowest latency levels that can be perceived by people? And the second, which is something of particular interest to practitioners, is how valuable are incremental improvements that are above that threshold? If you're making improvements below the threshold, it doesn't matter because they can't be detected. But we're interested in looking at what are improvements that are still in the detectable latency range. So what we mean by this is, let's say we go to a device manufacturer who has an existing device with 70 milliseconds of latency. And we say, you know, if you want it to be zero perceivable latency, you need to drop it down, let's say, to 10 milliseconds. So in other words, we're saying you need to have a 60 millisecond drop in the latency of the device. A device manufacturer is going to say, that's impossible. There's no way we're going to do this in one generation. The engineering is simply too difficult and too costly to do. What's more likely to happen is a smaller set of changes. We might go down to 50 milliseconds in one generation, then to 30, and finally down to 10. So what we're interested in answering with this second study are questions along the lines of, is each of these 20 millisecond drops equally useful? Are they equally noticeable by users of the system? So these are our two questions. So let's start by looking at the first question. Now, we're of course by no means the first to talk about interface latency. It actually goes back to the very earliest days of interactive systems. The famous work on this is Miller's 1968 paper, so almost 50 years ago, where he cites 100 milliseconds as a target for what's detectable by the user. And this became the standard accepted textbook value for interface latency. But it's clear that this can't be true in all circumstances. So let's take a look at why that's the case. I'm going to show you two videos of two different latencies. Okay, so here's a system operating with the first latency. And here's one with the second latency. Who thinks the first one is a lower latency? Show of hands. All right. Anyone think it's the second one? All right, one person. So what you saw there was 1 millisecond versus 100 milliseconds. So it's clear that 100 milliseconds is very detectable under the right circumstances. And in fact, more recent work has shown this. For example, Ng et al. At WIST a few years ago showed that it was actually down to 5 to 10 milliseconds were detectable by users. So that's an order of magnitude difference from what the classic textbook value says. So why is there this range? The reason it's a range is because we have very different tasks that have very different affordances. In particular, dragging versus tapping are two very different things. When you're dragging and there's interface latency, what happens is there's a spatial separation of hitting microphones, which basically has the object that you're dragging around trailing behind your finger, right? You see that gap. When you're tapping, it's purely a temporal thing. You have to think about when you hit versus when it shows up. Now, these two form the fundamental building blocks of most interfaces, which is why we care about studying them. The other variable that's worth examining is a direct versus an indirect interface. So when we say direct, what we mean is something where the input and output are coincident with each other, so something like a touch screen. An indirect interface is the opposite, so where you're interacting somewhere and you're looking at the responses up here. So what we wanted to do was do a single study that looked at all four possible combinations here to try and pull out the exact impact that each of these variables have, and let us do an apples-to-apples comparison using data that we generated on the same hardware. So let's take a look at what the hardware was. And this is the same hardware that we used for this study as well as the second study that I'm going to talk about. The hardware looks like this. It's the fast multi-touch system, which is described in detail in Lay et al. From last year's WIST. And it has a touch sensor, which is like a passive touch sensor at the bottom, and it has a high-speed projector on the top. Now, the touch sensor has no display. The only image is produced by a top projected image from this high-speed projector. The fast multi-touch system runs at a latency of less than 1/3 of a millisecond, and we have several software knobs that we can fiddle with to run it at a higher latency if we want. So we can simulate any other latency that we want to test. Now, as you can see, it's a direct input system, so we used a very high-tech piece of equipment to convert it, which is a mirror. The way that we did this was we have it running in direct mode. We simply insert our mirror assembly, and now we're running in indirect mode. The trials that we did across both sets of experiments were a series of A/B comparisons. So we allowed the user to interact using either dragging or tapping, depending on which session it was, with latency A, and then we showed them latency B. They then had two options. They could either tell us the final, their decision, which is the goal of each trial, which is telling us which is the more responsive latency, so they have to pick out which of the two is a lower latency. If they wanted to, they could go and see latency A a second time and then make a decision, but they couldn't keep going back and forth indefinitely. So it was a two-option forced choice study. How we picked latencies A and B differed between the two experiments, and we'll see when we get there how that worked. They interacted using this box, which also told them what latency was visible. Essentially, a trial in the study was what you guys did at the beginning of this presentation when I showed you those two latency videos, right? Except you didn't get to do it yourself, but it's the same thing. You see the two and then pick which one you think is the faster. Now, they're not all as easy as the one we looked at. Some of them are considerably harder. I can't actually show you the really hard ones because this projector system can't run fast enough to show the really small millisecond differences. So that's why we had to use the fast multi-touch system for the experiment. All right, so the first experiment. So remember, this one is looking at the first question. What are the lowest latency levels that can be perceived? So when we are asking that, what we're actually talking about is something called the just noticeable difference, or JND, which is a concept from psychophysics and psychology. And it's the smallest change in a stimulus that can be detected. Now, you can run one of these for any sort of stimulus, light levels, pressure, sound, whatever. In our case, we're doing the smallest change in latency away from zero latency that can be detected. The trials for experiment 1 were based on a reference and a probe. So this is basically where are we getting the latency values we're plugging into A and B in our experiment. The reference was always 1 millisecond, and the probe varied according to an adaptive staircase algorithm. For details, please see the paper, but the basic idea is you start off with the reference and probe being very far from each other. Every time they are correctly told apart and they get the faster one correct, they move closer together. Every time the participant gets it wrong, they move further apart. And eventually it'll converge at the point where they're barely able to distinguish the two. The design of the experiment had 12 sessions for each of tapping and dragging, and for each of direct and indirect. We ran 2 repetitions, and that was to fit it into a 90 to 120 minute block of time. So this gave us a total of 96 staircases, or about 8,500 trials. And our participants were drawn from the broader university community. We're all right-handed with the mean age of 28. So let's take a quick look at the data. So what we're looking at here is a chart that's showing the mean latency J and D. So this is the smallest value in milliseconds that can be distinguished from 0. This is the direct data, and this is the indirect data. So we see the best performance that we see is 11 milliseconds, and that's for direct dragging. And we do considerably worse for indirect dragging, but we're still doing better than we are for tapping. Those are at 69 and 96. And these differences that we see between direct being better than indirect and dragging being better than tapping makes sense based on the affordances of the devices. It's also worth noting that our values correspond with existing literature. The 11 milliseconds is within the 95% confidence intervals of Ing's 5 to 10, and that 96 is within the confidence interval of Miller's Classic 100. And it makes sense because he's talking about keyboard keys, right? That's an indirect tapping task as you hit a key on the keyboard. So that's the first study that we looked at. So using these to ground ourselves, we moved on to the second study, which is how valuable are the incremental improvements. The trials for the second study drew their A and B latency values quite differently from what we did in the first. And we based them on 60 hertz because that's the most common display refresh rate, and fundamentally that's the limiting bottleneck for latency of the system. You can process input, respond instantly, but if you can't redraw things until the screen updates at 60 hertz, it doesn't matter, right? That's your bottleneck. So running at 60 hertz means 60 frames per second. So every frame is 16.67 milliseconds. So what we did is we started with a variety of baseline latencies, and then we took those baselines and we subtracted an improvement in latency. So our baselines were listed here. So we started off with 16.7, right? That's our baseline value for everything. That's a single frame of latency. Then we had 2 frames of latency, 33 1/3, and so on, all the way up to 10 frames of latency at 166.7. You'll also notice 8.3, so that's half a frame of latency. And we put that in order to measure the impact of a 120 hertz system, which are also widely available in the consumer space. Our improvements are the half frame all the way up to 5 frames of latency. So this gives us a table, and each cell in the table, for example, this one here, says we're going to be comparing 150 with 150 minus 50. So in other words, our pair here will be 150 and 100 milliseconds. Now, not all of these entries in the table make sense. For example, you can't subtract 50 milliseconds from 8.3 milliseconds and have negative latency unless you have a time machine. So what we had to do was get rid of this chunk of the table, which leaves us with a total of 51 possible pairs. And this was our basic data set for the second experiment. The design was essentially the same as the first one. We had our 12 sessions for each of the techniques and form factors. This time we could fit more repetitions without tiring out our participants too much. And times 51 comparisons gives us a total of about 9,800 trials in our data set. And the demographics of the participants were similar to last time. So taking a look at the data, we see here a graph showing the percentage of correct responses. So this is how frequently for a given pair was the participant able to identify which was the lower latency in the pair. So this is the dragging data, and we see that they're doing particularly well. It's about 88% overall for direct dragging, for example. If we add in the tapping data, we see the performance drops off quite a bit. So we have a statistically significant difference between direct and indirect dragging, and we have a difference between dragging and tapping, but we don't actually see a difference between the two different conditions for tapping. Now let's take a look at this data in a slightly different way. So here's the chart that we had, or the table that we had earlier. And we're going to start with looking at the direct dragging data, and we'll come back to the other three conditions in just a minute. And what we're going to do is we're going to color code each cell according to the overall performance. So the first ones are chance performance. These are statistically indistinguishable from 50% performance. So in other words, an improvement that the participants were not able to identify. We're then going to go and color in the remaining deciles. So 60%, 70, 80, and finally 90%. So what's really interesting on this table is this chunk right here. Half frame improvements, so 8.3 millisecond improvements, were noticeable by our participants when you're starting at low baselines. So that's pretty remarkable. That's 120 hertz frame. We also see that essentially across the board, a single frame improvement is also noticeable, so no matter what your starting baseline is. If we add in now the data for direct tapping, we see a very different performance curve. In general, the 8.3 and 16.7 are not noticeable. So that means when you're tapping, you have to be 2 frames or better to be noticed across the board. We also see the performance is in general much worse. We have much less of the dark purple that we had for the direct dragging. This is the indirect data, and we see again that we're not doing those half and 1 frame improvements. I'm just going to put all 4 back up again, so these are the same 2 we saw earlier, and we see very clearly the differences between dragging and versus tapping. In the dragging, we have quite a bit of the dark purple. That's performance in the 90% or higher, which we don't see for the tapping conditions. So this is kind of summarizing the overall doing better at dragging and overall doing better on direct. So, in general, every study we did showed that the direct performance is better than indirect and the dragging is better than tapping. And if you look at it from a thresholds point of view, there's essentially an order of magnitude difference, 11 up to 96. So this means if you want to hide the latency in a device, it's better to have people tap than drag, and it's better to have an indirect system rather than a direct system. Now, of course, if you think about what current trends are in user interfaces, it's all this sort of stuff, right? It's all dragging on direct systems. It's dragging on touchscreens and swiping. So the interfaces that we're building now are highlighting the latency that's inherent in our devices. So this is something to think about as we design interfaces, whether that's something we want to be showing off is the poor latency of existing devices. Finally, we also showed that a 2-frame improvement is noticeable essentially across the board. However, smaller improvements, in fact, half frame and 1 frame, 8.3 and 16.7, are noticeable when you're direct dragging. So if you're building a touchscreen device, it's worth the engineering effort to shave off 1 frame of latency, because your users will be able to see that. Lastly, I have to say a big thank you to all of my wonderful colleagues, both at DGP and at Tactual, and hand things over to you for any questions. Thank you very much.
Thank you for the talk. Florian Block, Harvard University. So online games, when you play competitively, 60, 70 milliseconds, network latency is totally fine, right? And that's on top of the input latency. And the reason is because the application demands a lot of cognitive load from user. And so you don't really notice the latency that much. Now, would you think that if you did your experiments with a task that on top of just concentrating on telling the latency, gave the users a cognitive stimulus or a task in addition to your actual setup, do you think you'd get very different results?
Absolutely. I mean, cognitive load has a huge impact. The basic input primitives, if you think about doing things like launching an application or going back in your browser, things like that, aren't going to have that much of an inherent cognitive load. So those are the sorts of things where the latency is going to be really noticeable. But if it's something that you're having to think about, absolutely, you can get away with a lot more. So I guess it should be amended that if you really want to hide latency, make them do indirect tapping and think about it really hard before they do it.
Lane Harrison, WPI. I just had a question. Do you anticipate finding individual differences, like an effect of age?
Yeah, very much so. I mean, there's some people who are very good at it. We didn't see any real kind of all-star participants in the studies we ran for this set of them. Previous experiments we've done for previous papers have shown, outliers that are 1, if not 2, standard deviations off. They're generally people who are big gamers, we found, although it's just anecdotal. We don't have a large enough sample to do it. But I mean, any perception task is always going to have individual differences. So, and you're also going to, as you age, things are only going to get worse, right, for all of your perceptual systems. The cruel realities of time. So that is something that we are wanting to investigate, what sort of impacts aging has, what sort of impacts other factors, even gender, have. But yeah, we haven't done that yet.
Awesome.